Penultimate brown bag lunch seminar of the year. Our first speaker today is Alex Gerbich. He's a third-year graduate student working with Claude Andre, and he's going to talk to us today about a stiff ODE solver that he developed called WIN.
Yes. Well, thank you for introducing me. I'm so excited to be this afternoon's lunch entertainment. Today, like Brian said, my name is Alex. I'm a third-year astronomy PhD student. And today I want to tell you a little bit about an ongoing project I've been working on to accelerate the interstellar chemistry calculations and the fire simulations. Before I can do that, I want to tell you what the fire simulations are. So the fire simulations are a set of hydrodynamic galaxy formation simulations that are most well known for their detailed models for star formation and stellar feedback. Now that's what I spend like maybe half of my time thinking about are those models and that physics, but that's not what I'm going to be talking about today. Instead, I'm going to be talking about a small aspect of the code that is typically not even enabled when we run the simulation. And we'll talk about why in a second. And that's the interstellar chemistry, evolving the chemistry on the fly during the simulation. Now, the chemistry is important dynamically because the chemical abundances will determine the gas cooling rate. And so if gas is going to cool faster because it has maybe a more molecular component, then you're going to have, it's going to form stars much more quickly. So it's important dynamically during the simulation, but it's also important when you want to compare to observations after the fact. So you have a much richer data set after you've run the simulation if you've run the chemistry on the fly. And so if you want to make predictions, say for the carbon monoxide, the mass of carbon monoxide that's in a certain region of the galaxy, you have to run the chemistry on the fly. And you also, if you're going to be comparing to emission and absorption spectra, you want to make sure that you have the correct chemical abundances to do that with. So, but I said that it's typically like not even turned on. Instead, what we do is we'll use equilibrium tables, and you'll just look up the value of the cooling rate given a current temperature and density, which works to get you, galaxies that look incredible. But it, like I said, there are dynamical effects that come from doing this sort of time-dependent non-equilibrium chemistry, and also the sort of predictions that you can make are weaker without it. So why not do it all the time if it's so great? Well, when you turn it on, it turns out it's prohibitively expensive. Something like 98% of the work in some cases is spent just on doing the chemistry, which, as I said, you can get like mostly right results without doing it at all. So, we certainly want to address that if we want to include it in some of the larger volume or higher resolution simulations. Why is it so expensive? Well, at every time step, you have to go through each particle and evolve the chemistry separately, sort of do its own simulation of what the chemistry is doing. And that can be very expensive, especially when the chemistry that you're talking about is something like 157 different chemical species, all interconnected through an elaborate network of something like 2,000 chemical reactions. And of those reactions, importantly, you have contributions from heavy metal ions and molecules, which drive cooling in certain temperature regimes. And when I say heavy metal, I don't mean like metals that astronomers call metals. I mean like actual metals like iron and magnesium. So that's something to keep in mind. So even though these equations are very elaborate and complicated, when you're trying to solve them, their actual functional form is very simple. It's just a constant, this sort of rate coefficient, times the abundances of your different reactants. And so something that's this sort of straightforward to solve sort of leads us to believe that maybe there's some way to do it faster. Maybe we don't have to go through this whole convoluted mess of networks on the CPU. Could we do it instead on a GPU? Now, what might lead us to think that a GPU would be the right thing to do? Well, GPUs are really good at doing the same thing over and over again, if that thing is really simple enough. Because it has many thousands of processors to compare to like a standard CPU, which has like maybe 10 or 15 or 20 if you're on a cluster. So that's a huge increase. But those processors, they all work in sync with each other. They all have to compute the exact same operation at the same time. So that makes them really good for vector operations. So if you're taking like sort of two very long lists and you want to add them element by element, GPUs are like perfect for doing that. But NVIDIA designed these GPUs to work with this programming paradigm that they created called CUDA, which is an extension of C++ that lets you more flexibly program the GPU than just having like simple vector operations like adding things. You can write arbitrary code that will run. However, if that code has threads that will diverge and do different things, that's going to really slow you down. So ideally, you want to come up with algorithms where you can do the same thing on many thousands of threads all at the same time. That's what GPUs are good at. However, you have to keep in mind that they're also bad at things, like all things in life. So GPUs are bad at communication, sort of broadly speaking. For one, they can't see any of the memory that's on the CPU. So any of your arrays or any of your constants or anything that you're trying to integrate all has to be explicitly copied from the CPU to the GPU before you can do anything. They're two totally separate computers. Sort of like sending an MPI message, if you're familiar with MPI. If you're not, then it's fine. You have to copy it over. That can be really slow. In fact, it is typically the bottleneck for a lot of applications. Even worse, once you have the memory living on the GPU, it's really slow to access even when it's in RAM. Cache level access is really fast, like on a CPU, but reaching the global memory is slow. And last and sort of most importantly, your algorithms are limited because threads can't talk to each other. And in fact, you can't even guarantee that threads are going to complete operations in a given order. So they can only talk to each other if you group them in a block, and even then, it's very restrictive, the sort of communication they can have. So you have to sort of design an algorithm that keeps that in mind. So with all of that information about GPUs, can we still go forward and write an integrator? The answer is yes. But before you can do that, you have to pick what sort of integrator you're going to write. So there are two classes of integrators. One, explicit. So explicit integrators are ones where you can write the next integration step, y sub n plus 1. The name of the game is to find y sub n plus 1 over and over again as a function of all the things that you currently know, y sub n and the derivative at y sub n. So that makes it an explicit step. Meanwhile, implicit algorithms are ones that depend on information that you don't know yet, stuff from the future. So the derivative at y sub n plus 1, which you're trying to solve for. So typically, to solve an implicit equation, you'll do some, to solve it numerically, you'll do some sort of iterative procedure, like a zero finding algorithm. But you could do just one step of that and then solve for y sub n plus 1, rewrite everything, and that takes your implicit scheme to a semi-implicit scheme. So that makes it a little bit better for GPUs, but you still get a lot of the benefits of an implicit scheme. Now, why would you want to use an implicit scheme in the first place? Well, implicit schemes are really good if your system is stiff, which means that there are at least two timescales, one of which is much shorter than the other. And for an explicit scheme, to integrate a stiff system, you would have to integrate at the shortest timescale, which could be really slow. If you're trying to, integrate 1,000,000 years, but one of your timescales is like 20 years, you don't want to have integration steps that are 20 years long. It'll take forever to finish. Whereas with a semi-implicit or implicit method, you would be able to integrate that same 1,000,000 years in, say, steps of 100,000 or 10,000, depending on the stability of your system. So implicit schemes are really good for stiff systems. There's a tongue twister. If you take nothing else from this slide, you should associate the phrase explicit with a scheme that takes many small but cheap steps, where implicit schemes take much fewer, like larger steps, but that are more expensive because you have to compute something like, say, a matrix inverse, or the matrix of partial derivatives, which can be really expensive too. So what does a numerical integrator look like? So a general schematic is that if you're integrating an equation, so you're going to have some sort of integration loop where you're going to take a trial step, estimate the error in that step from the true solution, and then compare that to some tolerance that you have. If your error is small enough, then you're going to accept it. You're going to update y sub n, call it y sub n plus 1, and move on with your life. If the error is too large, then you're going to instead refine your time step, make it smaller, and then go through the loop again until your error is small enough that you can continue. I want to point out that specifically for this scheme, the RK2 explicit scheme, the most expensive part of this loop are these two pieces here, is just evaluating the derivative. So and that's going to scale as the number of equations in the system, linearly with that, because you just have to evaluate that many derivatives. So if we have a larger system, then you're going to evaluate 10 times as many derivatives. If you contrast that with the semi-implicit scheme, again, the whole picture looks generally the same. You have this integration loop, but now the expensive steps are evaluating the derivative. That's the same. But now you also have to evaluate the Jacobian, this matrix of partial derivatives, which can, in general, depending on how coupled your equations are, how sparse this matrix is, could scale like really badly. It's like you have to evaluate the derivative over and over and over and over and over again just to compute all of these different partial derivatives, especially if you're estimating it through like finite differencing, if you don't have a closed form for the Jacobian. So that can be really expensive. And even worse, you have to invert that matrix once it's done. So depending on the method that you're using, so when I coded it up, I used this Gauss-Jordan elimination scheme, which is like the simplest thing that you could do. And that squares is the size of the matrix cubed, which is like not great, but it's guaranteed to work even for dense matrices. So that's kind of why I went with it. So, okay, you invert that, those are the expensive steps. So you can code all that up, put it in CUDA, call it wind, and then see how it runs. If you do that on a simple test problem, so here we have the derivative, some initial conditions, you can solve this analytically and find this is what the equation should be, and in fact they match, great. You can compare the performance of your explicit scheme to your implicit scheme, and just like I was saying, sort of to drive home this point, is that the explicit scheme, hopefully you can see, took about a factor of 15 times as many steps as the semi-implicit scheme, SIE, and it took about a factor of 2 longer to do it. So those steps were cheaper, but it took more of them to get to the right answer. And both of them have converged to the same answer. These curves are lying on top of each other. That's why if you can't see the dark blue, you shouldn't. So, okay. And yeah, like I was saying, this system is stiff because there are 2 different time scales. There are these 2 exponentials, one of which has a time scale that, this term decays much faster than this other one. But even though the solution is dominated by this first exponential term, your explicit scheme will diverge from the correct answer unless you follow along really tightly with tiny little integration steps. So you can break that down a little bit by looking at how many steps were spent as a function of time in the integration. So to integrate from x to x plus dx, how many steps did that take? And yes, there's a pretty stark difference between them. Just, like I was saying, to really drive home this point, RK2 needs more steps to get to the same convergence level. Okay, we expected that for a stiff system. But all right, that's well and good for a toy problem, but I've gone on a whole numerical methods stint. It's time to get back to chemistry. I want to eventually solve chemical equations, not just random, sums of exponentials. So to start, instead of using the full 157 species network, I'm using a simpler, just 5 species, hydrogen, helium, and their ionization states network. The only interactions are ionization and recombination. So all of the rates are just sums of ionization and recombination rates. And so you can see that they're just a constant times some reactants. That's pretty cool. And I'll make the simplifying assumption, even though eventually the whole point is to evolve the temperature alongside the chemistry, that the temperature is fixed and the density is fixed. So the idea is to take a system that's out of equilibrium, evolve it forward until it reaches equilibrium, and then just use that as a baseline to compare how the code is operating. So if you do that for 4 different combinations of density and temperature, you can't really see them, but whatever, you find that, sure, it's converging to an answer. That's always a good first step. Second, it's converging to the right answer. That's separate, but also good, that you can calculate using the rate equations by hand. And third, that it's doing that on an integration time. This is time in years. That makes sense. So the equilibrium time scale, the physics is being modeled correctly. So wind is doing the right thing. So that was a sigh of relief. However, there was something kind of interesting that I found when I first ran this test. That contrary to this point that I've driven home 18 different times at this point, is that RK2 managed to converge to the right answer in fewer steps than SIE, and it took longer. So somehow RK2 is taking fewer, more expensive steps than your semi-implicit method. So what went wrong? Well, if we make the same plot of integration steps, the number of steps versus time to go from t plus dt, how many steps that took, you find actually that the system that we have for the temperatures and densities that I chose is not actually very stiff at all. And so RK2 requires fewer steps to converge. So okay, fine, not an optimal comparison, but we can still like play around and see where this goes. That still doesn't answer the question of like why these steps took so much longer than before. So to answer that leads me to investigation 1. So if we throw out the requirement that the answer we get is converged, and instead we just say, I'm going to integrate with a fixed number of steps. I'm not going to do any error checking. I'm just going to be super duper confident how I live my life. And instead change the number. So that's what each of these different lines are, is a trial run. Then compare how long it took to run with that number of fixed steps. You can estimate how fast each of your methods are. But when you do that, okay, sanity is restored. Blue here is, so on the y-axis is the time to solution, whether it's converged or not. And on the x-axis is the number of fixed steps that I took from going from t to t plus dt. You can see that, all right, very good. RK2 is about 31 times faster per step, but there's a bigger baseline. There's a larger overhead for RK2. And that comes from like the details of the implementation. I used like shared memory versus I had to load something into a cache and it took a little bit of extra time. Not a big deal. But the point is that this overhead is dominating the computational cost. So that makes it a bad example for comparing with a full time system. You know, that leads us to believe that maybe 5 equations just isn't enough equations to really make a good comparison. So what can we do to scale up without having to do all of the different chemistry processes? Well, you can scale the number of coupled equations by just repeating the ones that you have. So each set of 5 are coupled to each other, but then from there, they're decoupled from themselves. So you can have, you can pretend that you have 200 equations, but really you only have like, whatever, 40 sets of 5. And so if you were to look at the Jacobian matrix that you're going to invert for the SIE method, that would look like having exactly identical Jacobians of 5 by 5 size along the diagonal. So you have this block diagonal matrix. So if we do this, we expect that RK2 is going to scale linearly with the new number of like pseudo equations or something, because that's just more derivatives we have to evaluate. And we expect SIE is going to scale as the number of equations cubed, because this matrix is going to like blow up and it's going to be really big and we're going to have to invert it. So when we plot again the time to solution versus the number of equations, we see something that's even more surprising than before. This red curve, RK2, actually doesn't scale at all. Not only does it not scale linearly, it's almost constant. Whereas this blue curve is not scaling as the cube, it's scaling as the square of the number of equations. So somehow we're losing a factor of NEQN. And if you look a little bit closer at how busy the GPUs is, that's called thread occupancy, you're finding actually there are plenty of threads eager to take this extra work that you're creating. You're making a lot of new equations to evaluate the derivative for, but there's free threads that are there ready to take on that work and do it simultaneously. So you actually get a factor of NEQN from parallelism. Well, and so both of them are divided by this factor of NEQN. Okay, that's telling us that the GPU is too idle. It's not busy enough. It needs more work. So far I've been using just this grid of 4 temperatures and densities, but in general, when we're running on the simulation, we're going to have like 10 to the 6 particles that we're going to want to run this on. So can we scale that up? The answer is yeah. Again, you can just repeat these matrices that we had from before. The GPU doesn't know that it's already solved this work. You're just telling it to do the same thing over and over again. You can see how it scales. When we do this, we expect both SIE and RK2 to scale with the number of systems because they're independent from each other and they're just going to queue behind each other. When you do that, sanity, again, is restored. You start to see how as n systems, so when you plot the time to solution versus n systems, you see, for large enough n systems, when you're finally saturating the work on the GPU, you get this linear scaling. And here is what I was talking about when I say low thread occupancy. It's like we're increasing the number of systems by a factor of 100, 200, 300, and the time to solution is hardly increasing at all. That's free work that you're getting because the GPU had threads that were idle, waiting for something to do. However, there's actually something really subtle happening in this plot as well. The knee for both of these are at a different number of systems, which led me to believe that maybe the scaling is not from a thread occupancy, but rather is bandwidth limited. Because here we're having to copy more information to the device, to the GPU. We have to copy a gigantic n-cubed matrix. Here we don't have to copy that n-cubed matrix. Remember before I said that it's really slow to move stuff over from the CPU to the GPU. And so there's some ambiguity in this plot. Are we bandwidth limited in being able to move this data from the CPU to the GPU? Or are we occupancy limited? Are we not actually having enough work and we're limited by our scheduling? And so the only way to break that, you can't figure it out, just from looking at this plot, is to profile your code. And so to profile your code is just to look at how much time your code spends at like each line, and how much time your code spends at each line, and then figure out like which function is taking up the most time. And when you do that, you find that we actually are bandwidth limited. So that's a really good sign, because when we're running on the full simulations, we're not going to be copying back and forth so much. We're going to just copy once at the beginning of the simulation and once at the end, and then just let the chemistry live on the GPU the whole time. So that's a really good sign. So takeaways, don't totally ignore explicit algorithms. Even if you think your system is stiff, they can have value, especially when your system has varying levels of stiffness depending on the physical parameters that you're putting in. We saw that actually the RK2 was outperforming SIE a lot of the time. However, the full chimes network will still likely be stiffer than the one that I was using. If there are extra threads lying around, you should use them. So you should never be in the low occupancy limit. You're underutilizing your resources, and you're gonna, that's free real estate. You should take advantage of it. Last but not least, scaling tests alone can give you a really good intuition for what's going on in the problem. But you have to combine it with some sort of profiling tool to break degeneracies, like in the last slide when I was talking about occupancy versus bandwidth. Next steps going forward, I have to actually scale up to the full chimes network. Currently, I'm waiting to get the data file with all these different rate coefficients from the developer. He said that he would finish it 8 days ago, so hopefully he gets to that. No shade. After that's done, I have to actually attach it to the Galaxy simulations, right? My goal is to use the exact same API that Chimes uses. So then it's just like a transparent black box switch. There's that, like, fingers crossed, that's a smooth transition, but these things tend to always be harder than you expect. And then lastly, I want to readdress this matrix inversion step. So like I said, I just used Gauss-Jordan elimination. Before, I was actually using a linear algebra library like cuBLAS, which provides like something you just like give it a matrix, you tell me to invert it, and it'll do it like really fast. But it stopped working on Saturday, so I had to replace it. So I want to spend a little bit more time thinking about smarter ways to do this, especially taking advantage of the fact that the matrices are going to be very sparse, like generically speaking. However, there's some like logistical issues with using a linear algebra library. None of them are written for you to call them from CUDA. That's what I mean by having a device API. All of them are written to be called from the CPU. So then you like lose control flow control, and the CPU is it's being blocked. It's long. Yeah, I don't want to get too much into it. But anyway, I don't really like cuBLAS. And then last, I want to take the opportunity to acknowledge support from the Blue Waters Graduate Fellowship. Not only did they pay for my groceries and my rent for the past year, they also gave me access to their expert support staff, who've been really invaluable when I was learning how to debug and profile wind. I guess with that, I'll take any questions with whatever remaining time I have.
How did you compute the Jacobian from numerical?
Yeah, that's a good question. So analytically, I wrote out each of the elements of the Jacobian by hand for my simple 5x5 system. That's really easy to do. You can organize your rates equation, your chemical network, in such a way that you can do that programmatically, and that's our plan going in the future. It's like looping over each of the equations, and every time you hit a reactant, like add it to the Jacobian. I really want to avoid doing it numerically by just doing the finite differencing. So that's my goal, but worst case scenario, I'll have to do that. And that could also be a slowdown.
How much is swept under the rug with your rate equations? Gamma's temperature dependent?
Yeah, they definitely are. And the gammas
are three-body interactions ever important?
Yes, certainly. So in the full chimes network, you have much more complicated models for the different ionization rates. There are certainly three-body reactions. Sometimes you have interactions like on the surface of dust grains, all sorts of different stuff. So for my simple like 5 equation network, I don't model any of that. But what that's going to do is it's going to give you a derivative function that you can't just evaluate, you can't just write as a constant times two densities. So there will be like 3/4 of your systems that you can do that, and so then you should. But then for the last quarter, you have to loop through some chemical or some complicated physical model for like all the different dust grain physics and ionization rate changes. And then you still get a derivative in the end, and you can still do the numerical integration. It's just you have to do those separately. So that's kind of our plan when we scale up to chimes.
Questions for Alex? Thanks, Alex.
Oh, sure. Thank you. Hopefully it works.
Yeah.